If you've ever gotten onto an airplane, especially a really big airplane, and it starts hurtling down the runway at 100 miles an hour, I think everyone has wondered, how in the world is this going to actually fly? It weighs an enormous amount. You're heading to certain death at the end of a road, but all of a sudden, you're up in the air and on your way to your destination. Well, it's actually fairly complicated, but there's a part of it that's actually not too hard to understand. And it has to do with a principle called Bernoulli's principle. And what this says is that if I take the pressure, okay, that's the force per unit area on something, and I add to this 1/2 times the density of some fluid, air is going to be in this case, times the speed of that moving fluid squared, this is equal to a constant. All right. So, we've got a great demo of fans. So, the balloon actually sucks into where the wind is blowing. That's hard to believe. Usually you think, oh, the wind is blowing, this is where the pressure is going to be higher. But if we think about the Bernoulli principle equation, if the speed of the wind is high, because the fan's blowing, for this to be the same, the pressure is going to have to be lower. And outside where this wind is small, where there's no speed of the fluid, then the pressure is actually larger. So a balloon actually is sucked into where the wind is blowing. Likewise, if you're ever in a shower with a shower curtain, the water is coming out of the shower. That means the air is being pushed by the water, and the shower curtain sucks in. It sucks in again because of this Bernoulli principle. The air in the shower is moving, and therefore there's a lower pressure, and the shower curtain moves in. So what does this have to do with flying an airplane? Let me show you the cross-section of the wing on an airplane. You notice that it's curved on the top and flatter on the bottom. So let's think about the flow of the wind around this. The wind is blowing this way, right, because the airplane is moving that way. And along the bottom, this can just go straight, right? Because the airplane wing is flat. But along the top of the wing, the air has to take a curved path. At the end, all of this air has to stay together. You're not going to create a pocket of vacuum where there's no air at all. And the only way for this to happen is for this air to move faster. And this, of course, by comparison, will have moved slower. So think about Bernoulli's principle. If the speed of this air is faster here, for this principle to be true, this means the pressure has to be lower. Down here, where the air is moving slower, the pressure has to be higher. If I have higher pressure under the wing, lower pressure on top of the wing, you get a force, shown here in this diagram as lift, going straight up. There's drag, of course, because you did hit the top of this wing here and you're pushing against it. So there's a force that way too. But generally, this idea that the curved airfoil gives me lower pressure on top and therefore lift, and the airplane can fly. This is not the whole story. In fact, when people really started looking at this, they said, hey, well, this part's true, and there really is a pressure difference. Man, it's not big enough to lift a 747, but it still flies. So the physics for the rest of it is a lot more complicated, but this part's fine. It's just not the whole story. What does this have to do with a windmill? Well, let me show you. Let's say we take the same airplane wing, but instead of having it pointing right into the wind, which happens naturally because that's the direction the airplane's going, but let's say we bend it up a little bit. Now, notice that means that this force, which is already because of drag going a bit this way, is now going to go even further this direction. Well, if we now take this as the blade on a windmill, the wind is coming from the front, but really this blade is twisted. So the force on the windmill blade actually makes it go in a circle. Let's see if I can draw that. We're used to looking at windmills, right? Maybe some kind of tower, right? And then up here, there's a hub, and you have these long blades coming out. And we all know that a windmill goes around in a circle. Well, if I look at the cross-section of this blade, not this diagram, but the other way around, that windmill blade is actually facing at an angle. So as the wind hits it, the force on the blade, the lift force, is moving it to the side. The same principle that allows an airplane to fly allows the modern electric generating windmills to grow in a circle. This type of windmill, which dots the landscapes across the world, are basically airplane wings at an attack angle to the wind, such that when the wind comes in, it actually produces a force that makes the windmill go around. The same type of force that's used to make an airplane wing lift vertically. How much power can you get from a windmill? The obvious part should be that if I blocked a larger area compared to a smaller area, I'm going to capture more wind. Because the wind coming this way, this is larger. And if I look at the blades that would be going up, they have a certain radius, right? And this would have some smaller radius. The area of a circle is pi r squared. So part of the equation that will tell us how much power you can get from a windmill is going to be proportional to the length of the blade squared, because it's proportional to the area that the windmill captures of the wind. Twice the area, twice the power. That's why you'll often find very long windmill blades. That's part of the question. So besides just plain size and area, the most important thing for windmills is actually the wind speed. And there's a few steps that show about the physics, but energy goes as the speed squared. But the problem is you also need the pressure difference. You can't have the wind totally stopped, but neither can you have the wind go down in power at all. So power, which is energy per unit time, turns out to be proportional to the speed cubed. And this makes an enormous difference. Just think about it. Let's say I had a 1 mile an hour wind. That's actually too slow to get most windmills to go. And I doubled this speed to 2. My power would go from something like 1 to 8. A doubling of wind speed gives you 8 times the power. This cube root is extremely important. And that means if you're going to place a windmill someplace, place it where it's windy. And even just slightly windier will make a big difference in the power that you can make. So windmills are going to be very large in area, and they are going to want to capture the fastest wind. When you're along the ground, there's no wind blowing at all. right? The dirt doesn't constantly blow off. Occasionally it does, but along the ground there's no wind. The earth is stationary and the wind above it is stationary too. As you go higher and higher up in the air, generally the wind gets faster and faster. Since speed is so important to a windmill, you want to get up high. Let's look at an actual windmill in Windmill Tower Making Company. Wow, so here's the actual wind turbine. And if we look inside, you can see all of those bolts. What did you say, 28 feet underground this goes?
This one here only goes about 10 foot.
10 feet underground of cement, reinforcements, and reinforced concrete of it was a 28 foot by 28 foot pad spot. Because otherwise, all that wind pushing it, it's just going to fall over. Who knew all the stuff you have to do underground to be able to make this actually work? Right.
This one here has the power cable coming down. That actually will allow it to, it's just held by a hoisting grip on the top, free-handed, which allows it to go through its yaw and make up 5 rotations either way. So you'll actually see if this sits here and makes it around 5 different times, keep moving one consecutive, it'll actually shut down.
Because the wire will be unwound the wire. That is a good point. I'm glad someone thought of that. Can we look up inside? Man, can you believe it? I'm inside a windmill. All right. Wow. That's a bit of a climb up there. And I like the concept of how the cable just can twist.
It's just free-handed.
Yeah. Inside a windmill, 120 feet.
120 foot to the turbine.
120 feet up, 70 foot diameter. And 100,000 watts is right now coming through that cable.
Yes.
100 kilowatts. Really cool. Big one. So the commercial ones that are outside, going up the interstate, when you see them, they're 3 times taller than this. And they're making 15 times the power. All right? 3 times taller, 15 times the power.
They appear like they're spinning a lot slower, but I know in some of them you're looking at the tip speeds at 150 miles per hour.
Yeah, it looks smaller, but man, that's a giant circle they're tracing out. And once, oh wow, it goes around once every, couple seconds. That's a long way to go around that tip in a couple seconds. They're like airplanes. So, really neat. So making a tower is not as simple as you might have thought. After all, the wind's going to be pushing against this windmill, and that means there's a lot of force and torque on it. And actually, it's that force and torque on the windmill that causes it eventually to wear out or to have maintenance beyond its normal lifetime. Just like in solar power, to be able to figure out the economics, you have to know how long will it last. You made a capital investment, either in making the solar cell or in making the wind tower. And if it lasted forever, gosh, the electricity would be cheap. If it falls apart in a year, then it's just silly and stupid to even have done it in the first place. To improve that longevity, here is the engineering difficulty. So here's the ground. And the wind along the ground doesn't move really at all. You go up a little higher, the wind moves faster, 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 faster. Good thing. We want our windmill to have a fast speed. But if this was our windmill tower here, and here are our blades coming out, notice that when the blade is at the top of its journey, it's receiving a bigger force, and it's also therefore having a larger force trying to push it around in a circle. And when it's at the bottom of the tower, it has slower wind, so it has less force pushing against it, and it provides less of a force in the circle as well. Having your windmill put higher forces on the top of it all the time and lower forces on the bottom provides a torque. And that torque will cause problems in the gears that are turning inside the windmill. So let's take a look at what's inside a windmill. One of the keys is that you always want the windmill facing into the wind. And that's why the entire generator set is up in the air. The whole thing can swivel. If you tried to do this with gears and keep the heavy parts on the bottom, you'd wear them out for sure. But taking care of this inherent wind shear torque has been one of the greatest engineering challenges, which today has largely been solved. But when windmills first came into the vogue, say in the energy crises in the 70s, people said, oh, let's get renewable energy. Many of those first windmills that were made did not have this engineering problem solved. But today's systems are engineered and indeed will have these 20 to 25, or who knows, maybe even longer lifetimes. The windmills that generate electricity fall into the category of high speed, and because they're going very fast, they actually provide a low torque on the shaft that's spinning. You might not think that these windmills are high speed, but really you're just fooling yourself. They're so large when you see them up there, and since you can follow it going around, you don't realize just how fast that tip is moving. You do a bit of the math, and those things are going extremely fast. I want to contrast this to the more traditional windmill. This is called the American farm windmill, but the Dutch windmill is always the same thing. And those blades are not shaped at all like an airfoil on a wing of an airplane, but rather they're basically just slanted pieces of metal. The wind hits, and gee, there's a force that pushes it this way. These actually don't turn very fast. These fall into what we would call a low-speed category. But what they do provide is high torque. You can actually lift weights with these. You could grind grain by turning a giant millstone on top of a grindstone. And what the primary use, at least as the settlers went across North America, and many windmills do this for this very day, is they pump water. You can see here, you've got your water tank for your livestock. You've got some water source. When the wind blows, good. It will pump the water up into the tank. When the wind doesn't blow, well, you just hope it blows again before all the cattle get thirsty. Low speed, high torque, American farm windmill, or the grain grinding Dutch windmills that dotted Europe for centuries. Windmill technology has really progressed even in the last 15 to 20 years. And part of this is because we recognize the speed of the wind is paramount to the cube power. So you want to put your windmills where the wind is the fastest. And oftentimes that's going to be over large flat surfaces like oceans or lakes or seas. So putting windmills out in these windiest areas where also you aren't taking up valuable land where people are living or farming can be very important. And the evolution of being able to put a windmill at sea has also evolved. If the water is not there, you just dig your foundation into the ground. If the water is shallow, you pretend the water isn't even there and you do it the same way. As the water gets deeper, you have to recognize that the water force flowing through is going to be a problem. So you're going to have to put in some more intricate flow-through type tower structure. And in the absolute deepest water, you can actually design a windmill that floats, that has some stability to where it's at, but you actually have a type of platform that allows it to move slightly with the sea, but still stay vertical. The ability to do this and to have these things survive through punishing storms, yet still capture the wind, is another amazing engineering achievement. So that's what you need to know about windmills and their engineering.